In the last lecture, we considered the Chinese room and began to discuss some of the objections that have been made to it. I want to begin this lecture by saying what I think is at least part of its philosophical and scientific significance, and then we'll explore in more detail some of the objections, many objections that have been made to it, and the way the argument has gone on over now 15 years. It's important to distinguish consciousness, our subjective states of awareness, from our understanding or our ability to represent objects and states of affairs in the world. Philosophers have a technical term for this capacity of the mind to direct itself at objects and states of affairs. It's called intentionality. And intentionality is somewhat misleading because it makes English speakers think that it's got some special connection with intending. Like most confusing philosophical words, we borrowed it from the Germans. It's not a problem in German. But in English, you got to remember that intentionality refers not only to intending, but believing, hoping, fearing, desiring, wondering, whether, seeing, actually carrying out an intention to do something. All of those mental states, the mental phenomena there, are called intentional, and the phenomenon of intentionality is supposed to be separable from the phenomenon of consciousness for the obvious reason that many of our intentional states are unconscious. Often we have beliefs and hopes and fears and desires of which we're not conscious. Now, in the early days of cognitive science, people wanted to separate the problem of intentionality from the problem of consciousness, and a lot of people would have agreed that computers, at least the ones we built so far, aren't conscious, but they thought they do have understanding. They do have intentionality. Now, part of the power of the Chinese room argument was it doesn't rest on consciousness. It is not designed to show that computers aren't conscious. I think they're not, but that's a separate issue. The point is, the power of it is it shows they don't even have intentionality. They don't have any form of understanding, not just in virtue of implementing the program. Now, arguments have a logical structure, and I want to make the logical structure of the Chinese room argument fully clear because a lot of the criticisms didn't really understand the structure. It's really a very simple structure. The first premise of the argument is the definition of a program. It follows from Turing's definition of a program that the program is defined in terms of the manipulation of formal symbols. I gave you the example of zeros and ones, but they needn't be zeros and ones. Any system of formal symbols where the machine can identify a symbol solely in virtue of its shape or form is adequate for a computer program. And I summarized that part of the definition of the program using the linguist jargon. I say programs are syntactical. That's by definition, the program is defined in terms of the operation on formal symbols independent of the medium in which those symbols are realized. That's what I talked about when I said the symbols can be realized in silicon chips or water pipes or cogs and wheels or pigeons pecking, anything at all, provided that it carries out the steps in the program. But now there's another point we know from our own experience, namely, our minds have actual mental contents. When we think, we do use symbols to think with. I tend to think in English, though eventually I got to the point that I could think a little bit in French. But the point is, the symbols that I use to think with have a meaning or a semantics. So minds have more than a syntax. They actually have a mental content or a semantics. But now what the Chinese room argument reminds us of is step 3 in our argument. Syntax by itself, just shuffling the Chinese symbols, doesn't so far carry any meaning. There's so far no meaning attaching to the symbols. That is to say, syntax by itself is not the same as, nor is it sufficient for semantics. The symbols are one thing, the meaning is another. But now from those 3 it follows. From 1, programs are syntactical, 2, minds have semantics, and 3, they're not equivalent. The syntax by itself isn't enough. for the semantics, it follows that programs by themselves are not sufficient for minds, that minds are not the same as programs, but that's just another way of saying strong AI is false. That is, from the fact that the program isn't by itself sufficient for nor constitutive of a mind, we have shown that strong AI is false because strong AI is simply defined as the view that programs that minds are a species of program, that having the right program with the right inputs and output is sufficient for having a mind. Now, as I said, I thought that was kind of an obvious argument, and I didn't see any reason why it should meet with much dispute. But I have to tell you that it opened a Pandora's box of debates, and those continue. There are a very large number of not very good books and even worse PhD theses that have been written on this topic. And in fairness to my critics, I feel I have to go through a discussion of at least some of those so you will understand the nature of the arguments against me. And I think that's not just a matter of establishing an argument, but there are genuine philosophical and scientific issues that surround this debate, and I want to illustrate some of those in the course of answering the objections. I think what motivates the objections at bottom is a kind of residual behaviorism, is a kind of feeling that if it walks like a duck and it talks like a duck and it acts like a duck, then it's got to be a duck, and that's a mistake. That is, from the fact that the machine can talk as if it understood Chinese and answer questions in Chinese and behave as if it understood Chinese, it simply does not follow that it understands Chinese, because understanding is something that goes on inside the mind, and it carries a mental content and not just a formal syntax. However, I'm going to seriatim, as a series of steps, go through some of the most famous arguments against the Chinese room, some of the most famous answers. The first one that I heard I thought was very revealing. One of the leading figures in the field said to me, "But look, suppose we program you in the Chinese room to answer the question, do you understand Chinese?" So they give me this question in Chinese, do you understand Chinese? And I give back the answer, yeah, sure thing, I understand Chinese. Now, what does that prove? I think it proves nothing. Let's go through it. I get in a symbol that looks like this. You have to forgive my Chinese writing. This is a dialect of Chinese you probably won't recognize. I get in a symbol that looks like that. I don't know what it means. This is a meaningless symbol. I shuffle a bunch of other symbols. Unknown to me, that symbol means, do you understand Chinese? I don't know that. I look it up, and I give back another symbol in the same dialect that looks like that. And unknown to me, that symbol means, why do you guys ask me these dumb questions? Can't you see I understand Chinese? I've been answering questions in Chinese all week. A lot of semantic content packed into that symbol. Okay, what does that show? Nothing. That is, the fact that I can behave systematically as if I understood Chinese and can even answer the question, do you understand Chinese, in the affirmative, shows nothing about my understanding of Chinese. Well, let's, with that in mind, go through some of the other replies. I mentioned the systems reply, but another famous reply I call the robot reply, and here's how it goes. Imagine not a computer in a room by itself answering questions in Chinese, but imagine that we built a robot, and the robot could answer questions in Chinese, but it clanks around in the world. I mean, it actually bangs up against things and lifts things and moves around and walks around. Wouldn't the robot, just in virtue of the program, come to understand words of Chinese or any other language, because the robot is engaged in causal interactions with the rest of the world? I think the robot is no better off than the original machine in the room. Why? Well, imagine the example that I gave a little bit. I imagine myself in the room. Now we imagine a robot, but imagine that it's a great big robot, and inside the robot's cranium is a room. And guess who's in that room? Me. I am in the room, and I get in symbols that come from the robot's television cameras. It's got television cameras, and then it has the transducers that converts the information from the television cameras into a bunch of meaningless Chinese symbols that are meaningless to me. They come into the room, and I process them. Unknown to me, I am getting symbols from the robot's sensory apparatus, and I'm giving out symbols to the robot's motor apparatus that enable it to clank its way through the world. But I'm on a special hydraulic set of springs. I don't even detect the motion. I'm there in a locked room. I can see nothing, and I am processing these symbols. I am the robot's homunculus. I'm the little man inside the brain of the robot. But unlike the homunculus of classical philosophical theory, I don't understand anything. And if I don't understand anything, neither does the robot, because there's nothing in the robot as a locus of understanding except me carrying out the steps in the program. Well, another reply, which I thought was also revealing, and this gets closer to the nitty-gritty, was, look, it's true. Our existing programs aren't sufficient for understanding. But that's because they don't simulate the right features of understanding. But suppose we had a really complicated program that actually simulated the behavior of a Chinese brain. We had a program that simulated the behavior of the brain. You can imagine doing it down to the last synapse, or go to the neuron or synapse level, whatever is your favorite level. You just simulate the behavior of the Chinese brain. Now then, the argument goes, if that program doesn't understand Chinese, then you'd have to say native Chinese speakers don't understand Chinese, because what we're doing is having a computer program that simulates the behavior of the Chinese brain. Now, I think that argument is very revealing, because what it does, it combines the behaviorism that we saw earlier with the kind of formalism that we've been seeing that says the formal symbols are all that's necessary. That argument can't be any good, and let me illustrate why. Suppose somebody said, look, if you want to build a machine that'll digest pizza, just do a computer simulation of the digestive processes that go on in your stomach. But the computer doesn't digest pizza. What it does is produce a model or a picture of the digestion of pizza. If you've got this computer simulation running and you rush out and buy pizza and stuff it into the computer, it isn't going to digest it, because digestion names an actual causal physical process. And what the computer does is a formal model or simulation or description of that process. And I want to say what's true of the computer simulation of digestion is true of the computer simulation of cognition. Even if you simulate it right down to the last neuron and synapse, you're simulating the wrong things. That is to say, all that the computer does by definition, because programs are syntactical, is simulate the formal syntactical structure. But when we talk about the operation of the brain, we're talking about very specific causal processes, very specific processes that actually cause states of consciousness, and you don't reproduce those states by doing a formal simulation in terms of symbols. Now, I would have thought that point was obvious, but a lot of people don't see it, so let me hammer it home with a couple of examples. We don't know much about how the brain works. I mean, we're making some progress, but we don't really know very much. But there's some things that we do understand. We understand the effect of certain drugs on your nervous system. Now, not all of them. We don't know why alcohol makes you drunk or aspirin cures your headache. But we know some of the things that cocaine does. And one of the disastrous things it does is that it impedes the capacity of the synaptic receptors in the brain to reabsorb a certain neurotransmitter. It's called norepinephrine. And the effect of this is that because the neurotransmitter isn't reabsorbed, it tends to stay in the synaptic cleft, and this has a dramatic effect on people's state of mind. Okay, so you get the picture. We got this neurotransmitter. It's squirted into the synaptic cleft, and it's, well, I was going to say sloshing around, but we're talking about a small number of molecules. I mean, hardly waves of this stuff, but anyway, it's very small amounts of it. Now, here's the point. We could do a perfect computer simulation of that. That is to say, we get zeros and ones to stand for the different features of the process by which cocaine affects the capacity of the brain to reabsorb neurotransmitters. But the computer simulation doesn't get a cocaine high. And if you have any doubts about that, think of it in terms of actual models. I mean, let's do a computer simulation. Let's do a simulation where we use beer cans and ping pong balls, and let the beer cans represent the anatomical features of the brain, and the ping pong balls different colored ping pong balls can represent cocaine and norepinephrine. Now, this system of beer cans and ping pong balls doesn't feel anything because it hasn't got the right machinery. You can do a model or a picture of the operation of the brain at any level you like, just as you can do a model of water molecules using colored ping pong balls or golf balls, but you can't swim in a whole lot of ping pong balls because what you've got there is a model and not the real thing. And why not? Why don't you have the real thing? The answer is the one thing that's left out of the whole computationalist story: causation. The brain is a causal mechanism. The brain actually causes conscious states. And that's why a picture of the processes by which the brain causes conscious states, even though it might depict or model or simulate anything you like down to any level of accuracy you like, will leave out the essential element if it does not capture the actual thing that brains have. Now, I'm going to add this as a separate premise here because it's going to be important for the argument later. We're going to say, as a matter of how it actually works, we want to say brains cause minds. And that's just a shorthand for saying neurobiological processes in the brain, as far as we know at the level of neurons and synapses, cause all of our conscious life. Keep that in mind because we're going to come back to it. That's an important addition to the structure of the argument. Okay, so far we've considered three objections then: the systems reply that we talked about last time, the robot reply, and the brain simulator reply. Now, in fairness to my critics, I have to say there have been a whole lot of others, and I can't talk about all of them, but I'll talk about the ones I think have been the most influential and the most widespread. One that's frequently made, and of course is quite correct, is that in real life you couldn't build a program that would enable me to pass the Turing test for understanding Chinese if I was locked in a room. The truth is, you can't design a program that will enable a commercial computer to do that. We're nowhere near being able to do that, but I'm assuming for the sake of argument that in principle we could program a computer so that could pass the Turing test for understanding a natural language. Now, I quite agree, in real life, even if we had such a program, human beings couldn't carry it out in real times. It would take millions of years to go through all of the steps. But that's not the point. The reason we have these thought experiments in science and philosophy is because there are lots of things, lots of experiments you can't perform in real life. I mean, Einstein's famous experiments where he imagined that we go to the nearest planet in a rocket ship that goes 90% of the speed of light. That's a fantasy. We can't do that in real life, but it's a useful thought experiment. The reason I had the thought experiment is not because I thought we ought to build a room and lock me in it and see if we could actually do this. I don't have the patience or the lifespan for that, but because I wanted to illustrate a deep point. Even if we could, the syntax by itself is not going to be sufficient for the mental content or the semantics. Well, another objection, and this is an objection that I think is very revealing because it suggests to me people don't really know what a computer is. Another objection goes as follows. We're just talking about the existing state of technology, and many people say, yes, we agree, existing computers can't have intentionality. They can't really be conscious or have intentional states or understand Chinese or anything else. But wait till next year. It's like the old Brooklyn Dodgers. Wait till next year. We're going to have better computers next year, and they will actually have understanding. Now, what's wrong with that is that that argument, the wait till next year argument, suggests that we're talking about a particular state of technology, whereas the whole point of the example that I presented you is it rests on the definition of a computer. It has nothing to do with the state of computer technology at any given point. It has to do with what a computer is by definition. See, what technology gives us is faster ways of implementing the syntax of the program, faster ways of carrying out the computational steps. So the beauty of the Chinese room argument is that it has nothing to do with any state of technology. It's independent of any state of technology. Of course, you could always redefine the notion of computation, but computation is a well-defined notion, defined by Alan Turing in ways that I sketched earlier, and if that's the definition of computation, then we know as a matter of logic that computation by itself can't be sufficient for understanding, because computation is defined purely formally, and that has nothing to do with any state of technology. All right, another objection, and I'm losing count here, what are we up to, about 6 or so. Another objection to the Chinese room argument was, well, this objection proposed by Paul and Patricia Churchland, another objection they have recently put forward is, look, you might as well say that the electromagnetic radiation can never be sufficient for light, because if you go into a dark room, you can have machines that detect electromagnetic radiation but don't detect light, because what we call light is only a certain small fragment of the electromagnetic range. Now they say, why is it any different with syntax? Maybe you're just in the luminous room. The Chinese room is like the luminous room, and the guy's in there in the dark, and he thinks, well, light can't be electromagnetic radiation because we got electromagnetic radiation and no light. Well, that's a bad analogy for a very simple reason. What we're talking about when we talk about electromagnetic radiation is an actual causal property of a certain type of physical phenomenon to affect our sensory apparatus. What we call light is the effect of electromagnetic radiation on our sensory apparatus and on other optical devices. But this is the point. Syntax as such has no causal powers. Syntax consists of purely formal symbolic devices, zeros and ones or some other symbolic device, and the only causal power is the causal power of the physical medium. The only causal power that the computer has is to go to the next stage of the program when the machinery is actually running. But syntax by itself, unlike electromagnetic radiation, has no causal powers at all. It's only the implementation which has causal powers. See, there's an odd feature that's lost in much of these debates, and I want to emphasize it, and that's this. The brain is a physical organ. The brain is a kind of physical machine, and it has physical machine processes. Neuron firings at synapses are a type of mechanical process. They are a machine process. Ironically, in their urge to be materialistic, the computationalists are not nearly materialistic enough, because computation does not name a physical process. Computation names an abstract, formal, mathematical process that we have found ways to implement on actual machines. So the kind of computer that you buy in a store is indeed a machine, but it's an electronic circuit. But computation names an abstract mathematical process that you can implement or realize on the machine, but computation does not name a machine process in itself. Anything can be computational. You see, this is a deep point, and it has to do with the nature of computation. Computation exists relative to an interpreter who assigns a computational interpretation. Watch, I'll show you a very simple computer. This object is a very simple computer. It has a one-step program. The program says, stay there and don't fall off. Okay, that's the program, and it happens to be carrying out the program. I can easily upset the program because it's a rather Mickey Mouse computer. But now this is an important point. Computation is not the name of a physical process in a way that, for example, digestion or vision, human vision, is the name of a physical process. Computation names a formal or syntactical process that can be realized in an indefinite range of different computer hardwares. But that multiple realizability is a clue that we're not talking about something in physics. Computation does not name something in physics or chemistry. And that's the failure of the analogy between computation, which is not a physical process, and phenomena like electromagnetic radiation, which actually are. Well, I'll mention one more of these numerous criticisms. This one is due to Jerry Fodor. Fodor said, look, the whole point about computers is you got to have a mechanical implementation of the program. But in the Chinese room, you were cheating because the guy carrying out the steps in the program was an actual guy, was an actual human being, actual Searle in there going through the steps in the program, and that's cheating. Because the brain, when it is acting computationally, it does it without the benefit of anybody in there carrying out the program consciously. So if you have a conscious implementation of the program, that's not an implementation of the program. Now, when I first read that, I really didn't know whether to laugh or cry for Alan Turing, because remember, this is Turing's definition of that we're using here. And what Fodor, in effect, is saying is Turing didn't know what a Turing machine was. And that's a very nervy thing to say. You see, here's the irony of this. The word computer has changed its meaning. When Turing wrote his original work, computer meant person who computes, the way runner means somebody who runs. And when Turing talked about a computer, he meant a person who computes. And that's why his famous article is not called Computers and Intelligence, because that would be about people. It's called Computing Machinery and Intelligence. And computing machinery was opposed to computers. Now, in the way that languages have changed, we now call computing machinery, we call them computers. But in the old days, a computer was like runner or writer. It didn't mean machine that ran or write. It meant a person who ran or write. And what Fodor has done is, in effect, try to take our changed definition of computer, so computer now means machine, to say that a person computing isn't really a computer. But it's a totally arbitrary move. The definition of computation, which we got from Alan Turing, says any appropriate syntactical process is a case of computation, because that's how computation is defined. I mention that example because I think it's a symptom of the desperation of a lot of the people involved in this field. And as I said earlier, I don't fully understand the passion that this issue arouses. I am amazed both in my own case and in case of other people who have attacked the computational model of the mind, because I think it's scientifically and philosophically inadequate. But the extremity of the attacks and the passion that this arouses suggests that the conviction that people have that we're all computers is a bit like a religious conviction. It's the feeling that something very important, and maybe even more important than our research grants, is going to be lost if it turns out that we're not computers. Anyway, I could continue this list of criticisms of the Chinese room, but I want to open the discussion now further. I mean, we've already hinted at some of these larger issues, and let me now shift to what I think is the issue that has been underlying much of this debate. Remember Descartes. I said in our discussion of Descartes that the leading problem that we have with the Cartesian picture is we don't see how you can relate the mental and the physical. We don't see how you can relate the mind and the body. What's the relationship between the mind and the body? Descartes didn't have an answer. Now, one of the great appeals of strong AI, one of the great appeals of the computational model is we have an answer to that question. If the mind is a computer program, we know the answer to the question how computer programs are realized in computer hardwares. There are a very large number of people in the United States that make their living doing exactly that. They're called computer programmers, and they write the programs, which the engineers then put into a disk form or into some hard drive form, so that it's now implemented in the hardware of the computer. That is not a mystery to us. We know how it works. So it looks like we have a solution to Descartes' basic problem if we buy the computationalist story. Now, here I come out of the blue and say, yeah, but you guys are making a mistake. It can't be right because the program is purely syntactical and mine's got more than that. Now, their challenge to me is going to be the obvious one. Okay, if we're wrong, what's the right answer? If we're wrong in answering Descartes, what's the correct answer to Descartes? And I now want to give that. That seems to me what the Chinese room discussion naturally leads into. If the Chinese room discussion shows computationalism is not a solution to Descartes' mind-body problem, then the next challenge is the obvious one. What is the solution? And I want to give you the solution to the mind-body problem. Now, I have to tell you, it's not going to be a very big deal. I mean, we've had so many centuries of thinking, boy, that's a big deal, the mind-body problem, that when we actually get to the solution, it's going to be kind of disappointing, because I think it's kind of obvious, common sense solution. And if we didn't have 300 years, or more likely 2,000 years of philosophical baggage we were carrying around on top of our heads, it would seem obvious to us. Here's the solution. Ask yourself, how does it actually work? How does it actually work in real life? Well, in real life, what happens is you've got these sensory receptors. They're in your skin, and you're in your eyeball and in your ear, and these take in irritations. They take in stimuli from the environment. I hit this, and the sensory receptors in my skin pick up, are affected by the solidity of the table in front of me. Or I look at something, and my retina is stimulated by the assault of the photons. Now, there begins a series of electrochemical signals that go back up into the brain. We don't know the details of this, but we have a pretty good bunch of ideas about how it works. Take pains, for example. There are two types of pain receptors. They're specialized. Actually, there's the C fibers that I mentioned earlier take in signals about aching and burning sensations, and there are another type of fiber called A delta fibers, and they take in. They're specialized for receiving signals from pricking sensation. So if a pin is stuck into you, the signal is picked up by the A delta fibers. Now, both of these go up through the spinal column through a region called the tract of Lissauer, and then they go into the brain, and then there they spread out. There's some interesting differences. The C fibers tend to be localized more in the thalamus and other basal regions of the brain, but the signals from the A delta fibers go up into the somatosensory cortex, where you're much able to make refined discriminations. And maybe that's part of the explanation for the fact that our burning and aching sensations are harder to localize. It's harder to tell your doctor exactly where your back pain is, but it's pretty easy to say exactly where the pin is sticking into you. And nonetheless, the burning, aching sensations, those C fiber sensations, can be more distressing because they activate more of your nervous system. Okay, now what's the moral of this story? I just give you this as kind of a brief example of how the brain actually works as far as we know. The moral is, we're talking about a biological process. The brain gets signals from nerve endings. It takes those signals into the cranium, into the actual lobes of the brain, stuff that picks up from outside the central nervous system, and eventually the sequence that begins at the nerve endings causes an actual sensation of pain. You actually feel a burning, aching pain or a pricking pain. All right, so that's the first lesson, and it's an obvious lesson. Mental processes and states are entirely caused by the behavior of neurons, by the behavior of the brain. And that's an amazing fact if you think about it. All of our mental life, everything, pick your favorite, whether or not it's the wonderful taste of the Chambertin that you like so much, or it's the sound of the Beethoven symphony, or if you're not so optimistic, it's feeling the angst of post-industrial man under late capitalism, whatever's your favorite sensation. All of that stuff is caused by neurobiological processes in the brain. Now, that's just a fact about how nature works. And notice I didn't have to use any of the Cartesian categories. There was no talk about the soul or the mind. We're just talking about how biology works. We're talking about something that's as boring in a way as digestion. It's just this is how it works. And I like to think in very simple slogans, and I don't have a very big blackboard. So I put that by saying brains cause minds. All of our mental phenomena are caused by lower level processes in the brain. But now then, that leaves us then with this other question. Well, what are minds? What are these things that are with these thoughts and feelings and so on that are caused by these brain processes? Now, I have to tell you, I don't think that question is a very big deal either. But I may be being Philistine about this. Let's try it out. If you actually think about it, what's going on? Well, when I wake up in the morning from a dreamless sleep, I go from a state of unconsciousness to a state of consciousness. When I go from being without a pain to being in pain, there is a change in my brain. My brain now has a feature that it did not have before. It is feeling an unpleasant sensation. There is an unpleasant sensation of pain, a painful sensation. Now, consciousness in general, and pains and tickles and itches and visual experiences in particular, seem to me features of the brain. And let's write that down. What we're saying is, brains cause minds, but minds are just features or states of the brain. And again, we'll put that as a sort of slogan. Minds are features of brains. So the puzzle in the history of philosophy, if we look at it from the Cartesian point of view, is how can both of those be true? How can it be the case that brains cause minds if the mind is just a feature of the very thing that causes it? Actually, those kinds of relations are very common in nature. I think of the solidity of the table or the liquidity in the glass. Liquidity is caused by the behavior of H2O molecules. But the liquidity isn't a separate thing that's squirted out by the H2O molecules. It's just the condition that the system of molecules is in when it's liquid. So you have a situation where the behavior of the lower level elements, in this case molecules, causes the whole system to be in a state of liquidity, even though that state is a feature of the whole system that's made up of those lower level elements. See, this would have driven Descartes out of his mind, because it looked like you're saying, well then, somehow or other, minds are causes of themselves, because if the mind is part of the brain and the brain causes the mind, how can that be? And what I'm telling you is, not all causation works between discrete events in time. It isn't like first there's an explosion and then the building falls over. Rather, what we've got is a system is made up of lower level elements. It's made of molecules or neurons. Those behave in a certain way, and they cause a higher level feature of the whole system. Notice liquidity is a feature of the whole thing. I can't reach in and say, here's a wet molecule, I'll see if I can find you a dry one, because wetness and dryness don't exist at the level of individual molecules. It's the whole system that is liquid or solid. Now, analogously, I want to say it's the whole system that's conscious. It's the whole system that's feeling a pain or seeing something. It's not an individual neuron that's thinking about my grandmother, but it's a whole system of neurons, and yet though the lower level neuronal phenomena cause the system features of minds, the minds are features of the very system whose behavior at the lower level causes those features. It takes kind of a long sentence to say that, but I think the idea is simple, and I think it's what we know from all sorts of things about how nature works. To put it in words of one syllable, the way that we have found nature works is you explain the behavior of big things in terms of the behavior of little things. That's why we're so impressed by the DNA theory of heredity or the germ theory of disease. You got big things explained by the behavior of real little things. Higher level features of whole systems explained by the behavior of lower level elements. So now we've met the challenge that strong AI put to us. The challenge was, if the mind is something other than a program, then how can you solve the mind-body problem? You don't have a solution. And I'm saying we got a solution that's been available almost now for 100 years, since serious work began on the brain. We know that the relation between brain processes and mental states is a causal relation. Brains cause minds. But we know also that what we call our mental life, those are features and events occurring in our brains. So we can say both, and we can say without any inconsistency, brains cause minds, and at the same time, minds are features of brains. Now, I think that is the solution to the mind-body problem. Unfortunately, the easy solution opens the way into a number of very difficult problems, and those problems are, how does it work in real life? That is, how exactly do neuron firings at synapses cause all of the variety of our conscious life? And there we just don't know the details. But now notice what seemed a metaphysically appalling question. How can this be caused by a brain process? How can my states of consciousness be caused by a brain process? That's no longer an impossible philosophical problem. Now it's just an extremely difficult scientific problem. That is, we've gone from saying it's philosophically impossible that the brain processes should cause consciousness to saying we know it happens. It's just going to be very hard to figure out how it works in real life. What we then need is to get out of our obsession with the idea that there must be a quick fix, that some computer program is going to give us the secret to all of our troubles, mental illness, unhappiness, depression, everything, and begin to think how it really works in the plumbing, how it really works in the actual processes in our brain. Let me conclude this lecture with another historical thought, and that's this. If you look at the history of this subject, we have always tried to explain the brain, the most fundamental of our biological organs for explaining the character of our life. We've always tried to explain the brain in terms of the latest technology. We hope to solve the mystery of the brain by appealing to the latest technological gimmick. In my childhood, it was absolutely common to be told, brains are telephone crossbar systems. None of you are old enough to remember the days when a crossbar system was the height of technology. I look back in some of the books. Sherrington, the great British neurobiologist, said, brains are Jacquard looms. There are these wonderful, magical looms. That was the latest technology. Before that, it was said, brains are telegraph systems. Leibniz compared the brain to a mill. It's the operation of a mill. What you're going to do in the 18th century, that's the best technology you got. And I've even found Greek authors who said, the brain is like a catapult. It functions like a catapult. So if you put that in if you put computationalism in the history of the subject, what you find is it's just the latest in a long line of efforts to try to make intelligible to us in terms of some technological device that we do understand, something we don't understand, namely the actual operation of the brain. If there's one thing that I would like to come out of these discussions, out of this whole debate, it's a recognition that the solution to our problem is going to come through a serious, motivated, scientific investigation of how the brain actually works. We will not get the answer to that question by looking at how computers work or how jacquard looms work or crossbar systems or mills. We have to respect the brain as a biological organ. Thank you.